Okay, so I've tried to pull down the most important bits of the diagrams I had up there. So this is our constant airflow. It's a uniform airflow in this area that just blows to the right, constant speed, constant direction everywhere. We have a window of width d, which is what you're seeing here, and then a height h, which is invisible here because it's going up and down, towards and away from your eyes. And so, in the last sketch, I sort of drew the little what would you call it, a parallelepiped or a rectangular prism showing the volume of air that gets through in a time delta t. What I want to show you here is we're just going to draw a parallelogram, okay, and say everything in this parallelogram and within the height of the window is what comes through. So this air, if this length here, I'm going to say this length here, is v delta t. So it's the speed of the air, the magnitude of the velocity, the magnitude of this, and then delta t, which is the amount of time that passes. Okay, so now we've got this parallelogram, which is v delta t on this side, d here. And if you remember, maybe you don't, maybe you do, I don't know, you remember that if we take this angle here, the area of the parallelogram is equal to d times v delta t times the sine of this angle. Okay, so when this angle is 90 degrees, the sine is 1, and then you're just doing a rectangle. When this angle is 0, the sine is 0, and that's because d would be parallel to v delta t, and you'd get no volume or area through there. Okay, so the area would be this d, and d times v delta t would be the area of this top section here. In fact, I'm just going to go ahead and draw this in. I'm going to call this angle phi. And the reason why I'm not calling it's a lowercase phi, and the reason why I'm not calling it theta should be obvious in a second. So the area of this parallelogram is then d times v delta t times the sine of phi. But what, and then so then the volume flow rate through the window, we'll tell you what, we'll get to that in a second. But it's going to be easier if we, instead of looking at the angle between this direction, the flow direction, and the surface, we look at the angle between the flow direction, and what's called a normal vector. So this vector here I'm going to call n hat. Okay, let me try doing it again. A lowercase n with a hat on it. Okay, this is a unit vector pointing in a direction normal to d. So it is perpendicular. And what I'm going to do now here is show in a slightly bigger or slightly clearer way. Here's your surface, or here's your window, which is d wide at the top and then sinks h into the paper, and the velocity of the air is this vector v. N hat is a vector that is always perpendicular to the surface and has a magnitude of 1. Okay, remember, hat means magnitude of 1, so it's a hat vector, a normal unit vector. Okay, normal, you'll remember the last time we used the word normal was with regard to normal forces, and I told you back then, I think, that normal is math speak for perpendicular. So when we're talking about the normal vector, we're talking about a vector perpendicular to something. And if we're talking about the normal vector to this surface, we're talking about a vector that's perpendicular to this surface. So this vector here is perpendicular to the area or the surface of this window, which, the rectangle of this window. And so in this case, what we're actually interested in is instead of using this angle phi and taking the sine of it, we can take this angle, call it theta, and find the cosine of it. So what this actually ends up being is d, this area here that we calculated, is also equal to d times v delta t times the cosine of this angle theta. Okay? And so the reason why we use this, you'll see in a minute why we switch to this, but you can probably convince yourself that it's not very hard that if you have this angle as phi and this angle is theta, that phi and theta are going to be complements of each other, and that's why they have sine of one is cosine of the other. Okay, so we do that, and let me just move that up. Okay, and now what we want to do is we want to feed this into our volume. So the volume flow in delta t time, the volume flow rate through this window is delta V. I'm saying that's like, and I'm using delta because it's like a change in volume over this period of time, and that is going to be this area, which is the area of this parallelogram here, times the height of the solid beneath it. Okay, so remember, this is not just an area, because this window is not just a line, it's an actual rectangle, and so there's this volume beneath it that's just equal to this area times its height. Okay, so what this is equal to then is d. So basically, we just take this and multiply it by h. So I'm just going to put the d and put the h up front. dh, and then v delta t cos theta. Okay, now so from this we can simplify this a little bit. First of all, we can go down then and say delta v is your volume, okay, over delta t. Delta t, that's a little better. Okay, this is your delta t. We're just bringing this under here and saying this is equal to dhv cosine theta. So far, that's all right. Now, this window has a width of d and a height of h. Its area, then, is d times h. That's the area of this window, okay? H that way, d that way, shouldn't be hard to see. The area is dh. So you can actually replace this here with the area. So now this delta v over delta t is equal to area times v cosine theta. And here is where where this n hat and the theta become useful, because what we've got here is we've got the magnitude of v here, and we've got cosine of this angle here. And if you are sort of, if your brain is tickling and saying, a vector magnitude times the cosine of an angle smells like dot product, you're right, because v times cosine theta is equal to v dot n hat. Okay, in fact, I'm just going to show you that right now. Very easy. So let's do it with I'll keep black. Okay, so v dot n hat. Okay, remember, if you take the dot product of two vectors, you take one thing to do is take the ijk components. We don't have those here. We're talking about a more general way to do it. So you take the magnitude of each vector. The magnitude of v is v. You take the magnitude of n hat. Well, the magnitude of n hat is 1, right? So v, let me put parentheses around these things. So v is your magnitude of the v vector. The magnitude of n hat is 1, and then you multiply them by the cosine of the angle between them. So you can see now then the 1 obviously goes away, and this v cosine theta right here, this v cosine theta is equal to v dot n hat. Okay, so the volume flow rate, I'm going to call this delta v over delta t, equals the area you're looking at, the area you're measuring the flow rate through, times the volume flow, the velocity of the air at that point, this little v, velocity. Remember, the big V's, I'm trying to put the little wings and serifs on them to make them distinct, which makes them look funky. This was, by the way, when I was your age, Van Halen fans would draw this, almost this exactly, constantly on like their notebooks and stuff at school. It's just, so that I always think of Van Halen when I think of, that. Anyway, and this was back in the David Lee Roth Van Halen days. Okay, so v dot n hat is your rate of volume flow through this window. And what this means then, if you're satisfied with that, what that means then is if we scroll up and look at the analogies between electrostatics and the vacuum world, the rate of air volume flow through a window is equal to, or not equal to, but it's analogous to the electric flux through a surface. So what I'm going to tell you now is that if you have, and I'm going to draw this in sort of a more general way, you have an area, and I'm just drawing it this way to represent some area. This is in this is a 3D drawing, okay? It's a 3D sketch. Haha, I know, yes. I know how awesome I am at drawing, okay? So this thing has an area of A, okay? And here is the normal vector. And in some area, we have this uniform electric field that is angled like, I don't know. There's your electric field vector. That's a, you know what, I'm not going to draw one there. That's a horribly confusing place to put it. So put one there, electric field, da, da, da. Okay. There's the electric field vector, you know, that way. And imagine these are sort of going in 3D, so they're sort of like piercing through this thing at an angle. Okay? So with a uniform A, not uniform A, sorry, for uniform electric field, flux through an area is, okay, so here it comes. Capital Phi is our symbol for flux, okay? And because there are different kinds of flux, there's electric flux and magnetic flux. You could even do gravity flux, so there's no real point to it. The flux through an area, the electric flux through an area, that's what the subscript E is for, is equal to the area times that electric field dotted with the normal vector, the unit normal vector to the area. So what this is saying then is that it's sort of, it's like you're counting, you're measuring how much electric field punches through this area. If the electric field is going perpendicular to the surface, then it's going parallel to n hat, which means this, you know, this dot product, the cosine part, will be at a maximum. So if it's perpendicular, then it's just electric field times the area. So let me scroll this down one other little tick more. Yeah, that does it. Okay, so the special case, or one special case, is E times A if electric field is perpendicular to the area. Or actually, let's see. Probably better to say it's through a surface. Okay. Yeah. In fact, it's a surface with area A. So probably I'm sorry to spend time like nitpicking my stuff, but I do want to make sure this is clear. Through a surface. Okay, is this. And this assumes the surface is flat, so you're not doing any weird things with the area. Okay, it's a flat area, flat surface. Okay, so maybe I should say flat surface. Okay, a flat surface. And what's the other special case you can look at is what if the electric field is running parallel to the surface? And in this case, it's 0. So the other special case that's kind of useful equals 0 if electric field is parallel to the surface. Okay, and again, think of this like if you have trouble visualizing this, and it's hard because we're talking about something that is sort of intangible in a sense. You don't see it, and we're asking you to do this sort of semi-abstract mathematical concept based on it. So if you want to get an intuitive feel on this, think back to the electric. What am I trying to say? Sorry. Think back to the vacuum cleaner analogy. Okay. So think about the electric field. Instead of being an electric field, it's the velocity of a bunch of air molecules. You've got this window here, and you're trying to measure how much air comes through per second. If the air is going perpendicular to the window, you get a lot more air. You get the most air. If the wind is going parallel to the window, then actually nothing comes through. Okay. And if the wind is going at some angle, then you get some amount between the maximum and the minimum amount. And measuring the rate at which that volume of air is coming through is like the electric flux. So when the electric field is perpendicular to the surface, the flux is at a maximum. When the field is parallel to the surface, the flux is at a minimum. Anything in between, you get an intermediate result. And we'll talk a little more about how to apply this, how to use it in the next video.